see where we got last night. Pretty sure there were some bugs. Yeah. So R11, R12. RSP. So that one is busted. So this is right after the direct add. So the direct add is here. And then the next one is this. Yeah, I guess this doesn't work with RBP. Indirect indexed. Right, it doesn't work. Doesn't work unless you have a displacement. Yep, that asserts. So that works. Okay, look like this one has the same problem. So this is, why is it EAX? That's also weird. It's like I'm screwing up the Rex. The Rex byte is being screwed up. Oh yeah. No, I'm doing that here. This is 9, 10, 11, 12. So 13 is, okay, so this is RSP again. I see, that's the basic problem. So R13 is essentially the counterpart of RSP in the higher range. So let's see what we can do about that. Yeah, I guess this is really the same thing in both cases. Okay. Presumably also true for just doing a visual scan through this to make sure there's no other issues like that. Somehow I missed that last night because I was getting tired, but it seems that this is legit. So that bug was basically from when I extended from only being able to address the lower, the classic 8 registers to include the higher the higher 8 and the total set of 16. I didn't update the checks since a lot of the restrictions on addressing modes involving RSP and RBP also apply to, I guess, R13 and R14, since they're sort of the higher range counterparts. All right. I think this is probably right around, well, I think that's fixed. So let's start looking at some other stuff. The thing I was thinking about last night is while all of these sort of emit functions are, they're kind of clearly named and do exactly what they say, there's no real decision logic inside, they're not the most convenient to use if you're a compiler. If you're a compiler, you want something that's a little bit more abstracted from, for example, whether like like the difference between these two is essentially, I mean, it's whether the memory operand is the destination or the source. And one thing that's a little bit annoying with this sort of function interface I exposed is that like R and RM are always in a fixed order regardless of whether one is a source or a destination. So you would kind of like an interface where, for example, the destination operand is always first, kind of like an Intel syntax assembly. And similarly, another case is like this one. I guess there's both a 1 byte and a 2 byte case. But in either case, the case where you have an immediate operand, essentially the destination is always the RM field, and the R field is the RX field is cannibalized as an opcode, a 3-bit opcode extension. So you would kind of want to mostly write the same code from the code generator, regardless of which of these 3 encodings are relevant. And so my idea is we're going to write some macros that sort of do that. So for example, this here would be, this would correspond to this. 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 Something like that. And then for sib, let's see here. I guess that's not so. RAX. Why is this? No, that's not quite right. So this would be maybe like base x4 well, so for the first one, first the SIP guide, so that would be that, and then that, and then RDX, let's say, which would mean move like that, and this would then, or add, not move, and this would be RAX, I guess we would do 4x RDX, so this would be something like that. And I guess there's maybe a few other permutations, but basically you would write something like this, and it would figure out what to do in terms of like, oh, here's the rex thing that has to be emitted, here's the variant of the basic instruction, you know, there's basically, I guess 4 if you can count, oops, there's 4 if you count the 2 immediate size operand variants. And so it would do that, but you would mostly write the same code. The operands would logically always be in the same order. So whether the first operand is R or RM, the destination always comes first. So it would sort of try to uniformize that for readability and writability's sake. So yeah, so that's the idea. And basically what this is going to do is going to lean on a naming convention for the different instructions, so that we can do some token pasting in the macro to create the right function calls. So for example, there would be essentially, let's see here, there would be add R, add RM, and add I. Let's just ignore the 1-byte immediate and assume that I is always a 32-bit immediate. So you would basically have names like this, and you would have something like emit add R, emit add RM, emit add I, and there would also be like add I, extension add I, which we can go and look at what that is. Right, so immediate 32. Right, so this would be 0. And so, let's see, so using the existing terminology, this would be what that is. And then the I would be, it would be 81. Okay, something like this. And then we would do emit RR. You would have an op, a destination, and a source. And that would do emit rex, destination source, and then emit R, and then emit direct destination source. I guess we can try replacing the existing code, the existing uses of that. So that would be something like this case up here, or in this case here. So let's make sure these are properly updated once we replace them. So right now, that would be this stuff here. So instead, let's do RR. You know what, let me just change something else while we're at it. So we don't have to do all these casts, they're driving me nuts. Okay, still works. And then let's do, okay, so we wanted to replace this one. So that still works. These are in the right order. I did run it right. And then, let's see. Okay, so that works. So the other counterparts would be, so actually RM is the same. So I'm just going to define that for convenience. No, actually that's not true. What am I talking about? Operation, destination, source. So that should replace I guess some of these. Just testing the chat to see whether it's still working. Okay, it seems to be. Alright, so what did I change? Indirect. That'd be this and this, so that still works. You can't actually hear my my microphone? I can turn it up if it's too low. Alright, so that works. And the next one is indirect displaced. So I think indirect displaced is going to be MD. I'm probably just whispering because I'm sort of talking under my breath. But I will try to be better. RMD. I should do two variants here. there is a 1 byte displacement and a multi-byte displacement. And so this would be, let's see if that works. So that should be this case. I guess to verify that, let me just remove it. Now, I'm always suspicious when you keep running something expecting nothing to change. The null hypothesis is that like you forgot to rerun it, so who knows if it actually, okay, so that did actually disappear. And then so that did that, and now we should do the multi-byte displacement case. So that seems to work. Okay. Other cases, SIB, destination, source space, source scale, source index. So Rx space index, Rx space index. Emit indirect indexed destination source space source scale. Oh, I guess it's source scale, something like that. So this would be R sib destination source for X destination. At some point I'm going to fuck this refactoring up. Right, so RCX, which is, yeah, the second one, that's the base, and then the other one is the index. And we have to make sure that that's also true for these. So yeah. Okay. That looks good. And then we have to do a displaced variant. The combinatorics of this, as you can see, are a little bit unwieldy, but I think the alternative is that you have to essentially, whoever is writing, for example, the code generation for adding things would have to essentially replicate this in their heads and manually write it out. So I feel like that this is probably the way to do it. you only have to do this combinatorics once. You don't have to do it once for every instruction. You just have to do it once for the various combinations of addressing modes and encoding types. Okay. So that's it for something that starts with R, then MR. So this is where I guess it gets a little bit interesting, because now these are swapped, because now the destination is the RM and the other one's the R. And so I am sure I will screw this up, so I have to be careful. And then I guess it's indirect. And for the indirect, that also takes everything in the reverse order. Okay, so I guess we should go to this one, and we should generate the flipped counterpart. Identifier not found. Oh, I see. Because we're now flipping them. Anyway, how's everyone doing today? I expect that this part of the stream will be pretty chill, because I'm just sort of like filling out the matrix of things I know I'll need or will want. Right, so, yep, so you see now we have this here, where we're now writing 2Rx through this store to memory, and this seems to be right. Indirect. Displaced. I think the displacement now wants to go there. Yeah, that looks right. Dude, there's no way I'm not gonna fuck up this, because this is almost like copy and paste coding. But okay, so MD1, MD, now we have to do sib. so sib, so destination base, destination scale, destination index. And as before, this, well, things like that. And then indirect, indexed, source destination, base destination index, destination scale. Indirect. Yeah, so I guess let's do this. So destination. Destination for X. Cannot convert from argument. So sib should be base, scale. Oh. Okay. Ooh, access violation. I guess I should just make this big. Alright. So we should now have, okay, here we go. So let's just go and compare that. So we're writing to destination, which is RAX, plus 4 times source, which is RCX from source. Yep. So that looks right. And we have to do the displacement versions. Seems like I'm not actually testing these right now. So I should clearly change that. So if I do that, okay, that looks right. Actually, let me go through just as I realize it. For clarity, I'm going to rename these to source displacement. So that does it for these, I believe. Now we have to do the immediate versions. All right. yeah. So for the immediate version, you have an operation, you have a destination, and then you have a source immediate. And in this case, well, let's see. So, no. So operation, extension, operation. Is that true, though? I don't think that's true. If you have an extension bit, you don't need to use that crap. So the destination is always the RM with an immediate, because the other field is cannibalized in general for an extension. So I think that means source, yeah, source is 0. And then do that. And then we do a direct. And the direct goes from extension operation to destination. And then we do an emitting of that one. So we haven't actually tested that. I guess that would be a good one to test. So let's do that very first up here. Emit RI destination, and let's say 1, 2, 3, 4, 5, 6, 7, 8. Emit destination. Okay, clearly I typoed here. Oh. Extension underscore add not found. Okay. So that does the immediate. Does it for the rexes? Oh wait, it didn't do that, did it? Oh, it did. Okay. Now we have to fill in the matrix once again. Let's test that. So this is the basic version. And then this plus that. I guess let's go with something more distinctive here. Okay, that doesn't work. All right, I got it. So we now have this. That looks right. Okay, it also works with this one. This is exciting stuff, guys. This is riveting high-speed programming now, but I think we're almost done with filling out this code. So we just need to do the sibs for intermediates, and then I believe we're done. Destination base, destination scale, destination index. Destination base, destination index. Base, index, scale. I think that's the order. Index, scale, base, index, scale, base, index, scale. I guess let's test that. Destination plus 4 times, let's just take some fixed register like R8, and then debbeef. Okay, right, we can't do that with this one. By the way, when I started writing all this sort of manual, writing a crap load of cases out, then disassembling it and reading back in, I felt like a little bit like guilty that I'm not doing something more automated. But I think it actually works pretty well, because when you have something with very regular structure, like it's getting a little bit out of hand now because there's so many cases. But earlier, it was actually very easy to scroll through and look at any outliers. So it does kind of work okay. Okay, yeah, so RAX plus 4 times R8, and then deadbeef for the immediate operand. So that looks good. And I guess we now we're almost there. I think we have to do this one. Destination displacement. Byte displaced. I'm curious, how many of you people have written sort of compilers before? Maybe not like directly to machine code, but just compilers in general. Cool. So what are you saying? One function per instruction arity and a bunch of macros to assemble the arguments. Yeah, so did that work for x64? So one thing that's a little bit annoying about x64 is that because the operands have to go in the prefix, if they have the higher bit set, right? Like if they're from 8 to 16, it's harder just to do the thing where you just sort of, you first emit the thing for the base, and then you emit it for the arguments, and you just sort of paste those two together. You kind of have to insert the rex with the operands before the instruction. So you can probably make it work with that approach, but I tried something similar before in x86 where it was fine, but then x64 got a little more gnarly. So I think probably this is fine, honestly. Like it's a little bit I have to write this once, and now it should be easy. Yeah, and the next thing I want to do is like op. Let's see. Right, so R up one R. And this would be operation opcode. Operation. Okay, what the fuck just happened? So this would be opcode. And this one would be yeah. So the stuff you're talking about, I talked about this yesterday. Is that so this is a little bit of a philosophical rant for me, but anytime. So I spend quite a lot of time just reading other people's code, like open source or whatever, and particularly compiler code because that's sort of an area of interest for me. And even the people that are trying to do sort of direct code generation, sort of JIT compilers that aren't, trying to be heavyweight like LLVM, um, a lot of them have far too general purpose assembly infrastructure, right? Like honestly, especially something like a JIT compiler should not be making any decisions at runtime. It doesn't have to, right? Like it should have like the way to think about it is if you have a code path for generating say additions or something, usually by the time you're in that leaf of the call tree, you know exactly what you're going to generate. Like you don't know exactly what register, like that the register is maybe a piece of dynamic data, but in terms of like whether you're dealing with immediate or indirect and scale index bias, like the exact addressing mode, you know all that stuff once you're in that leaf of the call tree, and so making decisions is sort of crazy, but I actually see a lot of people doing it. I also think it leads to way more code because you then have to write this general purpose thing, and then you have to represent all this stuff as a data structure. Whereas the way I'm doing it here, it's essentially just a bunch of functions that you paste together, and they're going to get inlined, and the code is going to be really tight. So, yeah, sort of a mini rant of mine. Like maybe I can show you what I'm talking about if I can find. Someone told me about this GitHub Sub-Zero. I was looking at it last night after I shut down the stream. So I don't think this is the latest. Maybe, well, let's go look at the latest, I suppose. So yeah, this is apparently sort of a fast code generator for pNACL, which is their, it's their sort of low level but still portable instruction set for I guess for like porting native code to the browser. And they used to use LLVM, but they couldn't really afford to do heavy duty LLVM optimization. So they ended up, my understanding is, and I think this is something that a lot of JIT compilers that try to use LLVM fall into, is that at some point they want to do things their own way, and then at that point LLVM turns into a very unwieldy, high overhead instruction encoder where you have to set up all this data structure just in order to generate some bytes into a buffer, which is fucking insane. Um, so, okay, so this is way beyond, like the version I looked at is way older, but this is supposed to be their super high speed, pedal to the metal, no needless indirection thing. And then you look at, well, let's see if I can find where the instructions are. Yeah, like shit like this. What's going on, guys? Why are you doing this to yourself? I mean, okay, they do some higher level lowering, so maybe I shouldn't rag on this code specifically. Maybe this is actually okay. No, like you can see they still have this notion of a general representation of an operand, which means they then have to make decisions probably at runtime around how to do the encoding anyway. So, and this is honestly some of the better side of the spectrum. When you look at the people who sort of like, I'm writing a native compiler. Step one is writing a completely general purpose assembler, which I'm then going to use in a completely special purpose way. That's fucking insane. Anyway, I'll stop ranting about that. But it's something that kind of bothers me a little bit. Okay, upcode extension and then extension. So let's make sure that still does what I hope. So what were you writing your compiler for out of curiosity? Okay, that still seems to do the right thing. Actually, let me just... No, I think this is fine. Let's just keep it like that. So let's then replace this junk. Okay, so that doesn't work. So we should just be able to do up1r, add up1m, up1i. Oh, cool. So 65/2 to x86 jet. Yeah, I actually think a really good use for this sort of straightforward pedal to the metal approach, especially with like a one-press translator, is exactly... I mean, you can do it fancier ways, but if you look at something like MAME, they have this notion of recompilation, which they do some higher level recompilation things, but a lot of it is also just being able to generate code really fast without a lot of ceremony and interaction. All right, so what did I change? Did I break anything? Seems like this still works. All right. Okay, I think... So I'm pretty happy with this code now. I think. I mean, again, this is a little bit verbose, but... Oh. Let's remove this shit. Add to register. Yeah, I'm not going to worry about these right now. I'll add these maybe later. Or will I? I guess I could do this as D. And this would be like... fuck it. Maybe I'll do this. Otherwise I have to context switch back later. we need rip d. So this would be okay. So this would be emit our indirect indexed. So destination, destination, source, x1 RSP. No, you can't multiply RSP. Oh, right, that's why we're using it. It doesn't actually make sense. Just why that field is used. See what that did. So rip relative addressing works, pure displacement addressing works. That's all good. What was the other case? If the source is RSP and then you do, I see, so this is essentially emulating. All right. What is Riz? What in the fucking world is this? Huh? Riz? That's not a register. Okay. Pseudo index registers. So let me just verify that that was actually what I did. What in the world? I think it's because I'm trying to use RSP as the index. Oh yeah, I think this actually means 0. Oh yeah, that's what it means. It's just a weird way of encoding it. If you look at Let's see. Right, if you look at this here, no, because that means, oh, so that's mod RM. Right, there's this none thing here, which is if you have an RSP, this basically means none. So I think it just means 0. Like if you don't want an index register, then you do that. So it's a little bit weird. Like I would expect, rather than writing it this way, I would expect them to write it just like add keyword pointer like that, I think. Yeah, okay, so I'm right. It is that 0. It's just, it corresponds to this, when the index in the sib is that. I'm just not used to, I guess, seeing it that way. Like normally I'm used to seeing a little more cleaned up, human-oriented disassembly than that, but I guess it's useful that they're not, they're trying to be sort of lossless in their encoding, even if it all just means 0. Alright, so let's re-enable this. I thought I screwed it up, but that actually seems perfectly correct. So what am I doing here? Emitting, so this would happen anytime the source is RSP. So if we go here, yeah, that's just stupid. I mean, the new assembler is a piece of work, and not in a good way, honestly. Like, there's so much. I mean, there's a reason no one uses gas for actually handwriting assembly. At least no one who's sane. Everyone uses, like, I guess nowadays NASM or YASM, but holy shit. All right. So what was the case I was doing here? Right, this one. So that's interesting. You can see it handles this one correctly. So in theory, what it's writing here, it should really write this if it was consistent. But I guess because this is like the standard encoding of just indirect RSP, it pretties it up. But this is really like a SIB encoding, as you can tell from the multi-byte, right? Like this is the mod RM byte, this is the SIB byte. So even though it looks like a plain mod RM indirect encoding, it's actually SIB under the hood. So it's fucking weird why it doesn't choose to write this as that, because that's how I encoded it. I wonder if I make this like x4 rather than 1, I wonder if it actually will then choose to write it differently. Okay, so now it does. So now it does ris4, but if I have this, it doesn't. So it's like it has a canonical encoding, I guess, of 0, which is like x1 times RSP. But I guess anytime it's not that, then we get that weird pseudo register. Okay, I see. That's good to know, although that's kind of weird. All right. So that was that part of the spectrum. I guess we also have to I guess there's also a pure. Guess we could try doing the flipped. Frankly, I'm probably filling in too many of the combinations at this point, but I guess I'm being a little bit obsessive. So this is in, this is out. That all looks good. Okay. Oh God, I guess I need the immediates as well. Okay, let's just finish it. In for a penny, in for a pound. Wait, what? What is this doing here? Shouldn't that be DR? Yeah. Okay, so DR, this one, and then we need these variants for DI and RI. For these, source destination. I guess it's actually 0 in both cases. And then displaced. The source is extension. And then emit for source immediate. So displaced, destination displacement, and then emit for. And for this, we have to see the same deal. Chance of this working very low. Okay. So let's do D, I. So we do okay. is moving directly to a displacement, and this is moving to a rip relative address. Okay, so that works. Holy fuck, guys. That's a lot of error-prone copy and paste coding here. There's no way I'm ever going to be able to eyeball a typo. So let's hope I didn't make any mistakes. Yeah, as if. All right. Okay, so we have these definition macros. And to go back to earlier, I think normally the way a lot of people would do this is using table-driven techniques. Certainly table-driven techniques have the advantage that if you want to do indexing based on dynamic data, then that's sort of straightforward. I think in my case, I'm going to stick with what I'm doing here. So the way you define the instruction like this feels a little bit tabular. So you don't have to manually write a bunch of code, but it's not actually generating tables. It's just generating functions and enums and stuff like that. So yeah, I guess that's kind of interesting. So we can try filling in a few other cases. Actually, there's some special instructions we haven't covered yet, like branch instructions that use condition codes, and also things like mul that don't have an immediate operand, but do have a like an extension, opcode extension. So that's probably worth covering. But yeah, let me show you at least how you can do other basic instructions. So let's just go through the list. Add, and then there is and. So and is 81. What? No, I want the RM. Right. So this bottom one is what I call R, and that's 23 in hex. And then the M case is when RM is over here, so that's 21. And then the immediate version I guess is 81 with a 4. So realistically, I think what we're going to do here is, rather than trying to go through the whole table or write some code to auto-generate it, we're probably just going to... Oh, not 12, 21? I see. Okay, good catch. Rather than trying to auto-generate all these macro instantiations, I'm probably just, as I start writing the full compiler, I'm probably just going to go in, as I'm generating code for the different cases, I'm just going to go look them up and fill them in right there. I think one of the advantages of that is, first off, I don't get stuck in this sort of shitty data entry work, very error-prone. If I interleave the work sort of incrementally with adding the new table entries and writing the corresponding compiler code, it means I also can test it right then and there in the real use case, and so hopefully it's also less error prone. But anyway, yeah. All right, so that would be an example. Okay, so one case I just realized we haven't handled is something like mul. Multiply. I guess imul is another one we can do. Right. So mul has an implicit operands, right? Like RAX is always the lower bytes of one of the operands and also the destination, along with RDX for the destination. So you can see it has this operand extension, even though it doesn't have an immediate operand, which is normally the case where you see these operand opcode extensions. So we probably need a special case for these. Which may be a little bit awkward. Let me think about how to encode that. I guess there's not that many addressing modes we can use with this. So I think the way we're going to handle that is we're going to have something called 1x for extension, and we're just going to essentially write this as, so this would be F7 4. And then in order to call it, I think basically you're going to write it like this. Mol rbx will mean mol rbx. Well, you still have, no, so this would be that, and then, oh god, here comes the full combinatorial matrix again. Hopefully we're done soon. And so on. Okay, let's just do it. That's not too bad. So XR, only a source. I think we can just put 0 here. This has to be an X. And then the direct operand, we provide extension operation X. And actually, let's just test that first before we go crazy on the other cases. Yeah, I'm starting, well, I don't know if I have second thoughts about these macro. I actually feel good about these macros, to be honest. But yeah, the alternative is that everywhere in the code generator you have to keep a mental model of what order of the operands should be used in a given case. So this is hopefully a little better. But yeah, let's try this. Emit XR mol destination. Okay, so that's mol Rx, Cx. Okay, so that works. Mol emit XR. Oh, this seems like the wrong operand order. So I would expect this to be destination plus, but the thing it's multiplying by here. Okay, so it is multiplying by that. Yeah, it's always multiplying by R8. Okay, that is what I wanted. Never mind, false alarm. Okay, good stuff. Okay, I'm just gonna take a quick breather because this is just a lot of mind-numbing work. Okay, so what do we cover now? Do these, we can do multiplies. I think the next step is doing control flow, which is encoded in a slightly different way. Let me go and remind myself. Okay, yeah, doesn't look like they have a good tabular listing of the condition codes. Neither do these guys. Let's see, x86 condition codes. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, okay. And then let's create some aliases. Okay. Let's figure out how these things are encoded. Oh god, this is fucking awful. You see how the opcode is not in monotone order. They're like fucking alphabetically sorting it or some shit, which is not what you want. Okay. Okay, maybe I'll look at the NASM manual like Tom suggests. Don't see it. Oh, NASM appendix. Is this the one you meant? Okay, condition codes, I see, so they're here. Okay. So I think, yeah, it's consistent with what we did. Let's do JCC. Okay. So I guess one thing I need is like, I want to be able to say, maybe C for conditional, and then would be like, let's see, so some of these, this is like CM. I guess this would be J. What's a JI? And it would be 80. I'm going to register. let's see. So this is like a code segment offset. So it's not really an immediate, or is it? It's kind of like an immediate or a displacement. Okay, and I guess this would be something like emit C I J is, let's say, non-zero. And then an offset. What's the best way to do that? I wonder if I can use the existing upcodes, like for example, this would just be J 80 0, and then I do this. This essentially means emit now, because there's no mod RM, so we do need something separate for those. Getting a little bit worried about the combinatorics, I mean, which are already, there's a few hundred lines of this crap. Okay, let me read this a little bit. I guess you could do something like emit CI emit I jump immediate. This would be like and then there's something like this, which is just a normal emit x m jump. Alright, so for some of these we just use a standard encoding format. For some of them, I guess we need something new. slightly new, like this. Okay, so that handles those cases, I believe. And then for the conditionals, I think the way we handle the conditionals is we do this and then not 0 and I, and this essentially means emit j, and then passing this as an argument. So let's just write that out. Operation, condition code, immediate. For control flow, we don't, I believe, need rex, so we can just we can do operation ci, and then emit for the immediate. Okay. Sorry, I'm just kind of trying to think through how to not proliferate too many cases, but I think let's just get started. Let's just do actually the plain jumps, which take a single immediate operand, which we don't cover right now. think this is right, although, because this is sign extended. Right. And then the other case was it something like JCC. Let's go back to the NASM. JCC immediate. J 70. I guess there's no operand extension. And so we want operation opcode extension. Okay, CI, so this would be like jump if not 0 by this offset. Okay. So the macro is probably wrong. So this is the CI. Let's pretend there's no extension now. We can add that later if necessary. Jump if not 0 and then go here. Oh, I should have done an emit for. No, I did do that. What the heck? Oh, I see. Now it got out of phase with the instruction. So, okay, so this one is the 1 byte variant, I suppose. What if we have a rex? Does that change anything? I don't think so. I think rex bytes actually apply to this case. Yeah, it does not. I think rexes in general don't apply to the control flow instructions. I'm not totally mistaken. Okay, so what's going on is this variant is actually a single byte variant. Yep, it says that right here. So actually I want 0f. Okay, we need this one. We need to emit the opcode extension, which is 0f, because this apparently okay, I'm totally off in the weeds now. No, that is actually correct. But that's for a byte extension. Let's ignore that. So it would be so we call it I1. This would be 0f80. Okay, that's still not quite right, I think. No, it's 1, 2, 3, 4. But it's not interpreting it the way I expected. Well, that is right because it's sign extended. So let's Is it because of the interpretation of this? Let's just go and look at this. So I'm using 80. Oh, I think what's happening is that the encoding is relative, but the disassembler is printing it absolute. I see. So because of that, actually, a good way to test that theory is that if you do this, it's actually going to print different values. Yeah, okay, so that's it. It's because the encoding is relative to the instruction pointer, but it's printing it in sort of absolute coordinates when it's disassembling. All right. Let's just ignore that for now. Yeah, you're right. because I'm just passing in a binary file. I think normally it would do the section offsets, but the sections are implicitly just at 0 because it's a raw binary. This isn't too bad. Like, being able to write stuff like this, I mean, you can write helpers to do the offset calculations and relocations and stuff when you're, or backpatching when you're writing your code, but like, this is kind of pretty close to expressing the intention of the compiler writer at this point, I think. Although I realize it looks a little cryptic if you're not up to speed on what these shorthands mean. Okay. I know I've been saying we're done with the emitter for a while, and it's been like 2 hours. So I think we're almost done. Like, honestly, we could have done like a nice little expression evaluator using what we had before. But now we have control flow, and I think that's the big missing piece. Actually, I think one case I'm missing is related to move, because move have some special addressing modes to handle 64-bit operands. So even when you're in sort of 64-bit mode with a rex prefix, you'll note that all the displacements and immediates are still 32 bits. So the question is, how do you actually get 64-bit quantities into registers? And it turns out that move has some special case addressing modes for that. Yeah, like this one is an example. And then there's the M offset stuff, which is for doing, like an indirect. That's a 64-bit. I think there's also a 64-bit immediate. Oh, did we already cover that? Where are the immediate cases? All right, here. So bx, let's see, bx with a rex of, okay, so that's interesting. So if you're, okay, I guess we can actually test that. First by making a bit of a mistake, I guess. So if you do move, this is the register to register, which would be, let's find it, this one, 8B. Okay, so that works. And there's also, so that was 8B. Now we need the one where they're flipped. So that would be this one. No. Alright, you can only do it for RAX in this case. Okay, here. So that's 89. Okay, so that works. And then there's a special case with a MOF. Which is A3. I feel like these should be special cased, right? Yeah, I think there should basically be like a move RAX special case because of how different these are. So this would be move RAX I. No, so that's not a special one. Destination register, source immediate, and then right. So this would be emit rex. Well, let's pull these up. Guess let's test that first. I made a mistake here. 8, 16, 24, 32, 48, 56. Why am I brain dead? Huh? Anyway, so let me just check something. 8, 16, so that's 16 to 24, 24 to 32, oh, 40, 48. Yeah, 40. But by the way, this is not like the first time I've accidentally skipped that I've accidentally skipped 40 when I'm doing those multiples. I don't know why. Anyway, um, all right. So we have racks from off. That's A1. Yeah, that's probably it. So that's A1, and then for the reverse case, it's A3, it looks like. Guess let's test those cases. Move Ri, so it's like RBX, and let's do a big one. Move apps. I have never seen that mnemonic before. Oh, this is another gas. What is up with gas and their insane fucking mnemonics? Alright. But anyway, it seems to be doing what I'm expecting it to do. And then the other one was emit move rex off. Actually, let's just, rather than moff, let's just call it off. Right, so let me give it another nice big offset. Okay, that looks right. This also looks right. Those are all as well in the world. So now we can deal with full 64-bit immediates and displacements, which is good. Okay. At some point I have to get on the end of these random encoding things I haven't accounted. But I think we're getting, so I would say the one thing I haven't done at all is that pretty much everything I've done assumes you're using the full 64-bit registers. And that's somewhat intentional. I think I can come back to that later. Although potentially it will multiply all of these additionally. I have to think about maybe a way to restructure that. Maybe write some, I could write some Python code or something to just generate a bunch of these instantiations. Because you can imagine having like, you know, emit 32, blah, blah, blah. And now you're dealing with the non-Rex counterparts or something. But for now, let's just do pure 64-bit. I think that's good. Anyone have any questions so far? I think I'm going to take a bit of a breather now that I'm seemingly done with this before I dive into the compiler per se. Maybe I'll fill in some more of these random instructions like cmove. Good old cmove. And I guess there's also setcc. Maybe looking at some of those concrete cases will show more stuff we overlooked. Oh yeah, so that's definitely a case where it's not just a case of immediates. Oh my god. So do we really need to do the full range of these? That's another combinatorial explosion. I really need to rethink some of these, the way I'm setting these things up. Seems like a lot of it could be shared. The problem is macros can't generate macros in C, unlike in Lisp, so it's hard to abstract over the commonalities here. Maybe I should just write some Python code to generate this crap. What about set? Templates? Don't think we're going to use templates. I'm also not sure it really helps. I mean, yeah, I guess it could help here. Oh, I forgot about that. The only possible operands. So if you say rex on one of these, what does that do? Is it like the lower? Cannot be encoded to access the following byte registers if rex prefix used. Okay, so you can, so when you use that, you can only do the lower bytes of those registers. I guess that's fair. Alright, just going to take a quick break. I think even though for cmove and apparently some other things I need to potentially add more crap, I think this is more than enough to get going with probably a full compiler and then some. So I'm going to take a quick break, get some food just for like a few minutes, and I'll be back and we will go into the compiler. I will quickly do a gist of this thing with the instruction coding. Just one sec. I'm trying to log into my. I lost all my session cookies for websites, so I'm having to two-factor authenticate a bunch of stuff for the first time, which is a pain in the ass. I think I just realized I have tabs instead of spaces turned on. Alrighty. I guess let's get cracking on some higher level stuff. What the heck is this? Maybe that's the virtual spaces thing. Oh yeah, here we go. Okay. Okay, I think I will probably start from the other end now. now that I did the code emitter, which for me was like, oh, that'd be fun to do. I think I'm going to start from the other end just with lexing and parsing and stuff. We're going to try to do something basic before we go too extensive with the language design. To just do, start with a basic expression language, generate code for that, and then just kind of build out from there. I do want to make a little bit of an advertisement for this book, which, I mean, there's a lot of compiler books. If you guys are interested in compilers that are kind of very practically oriented, the one I recommend, which is not, it's not really focused on, no, that's not the edition I'm looking for. Which one? Now there's obviously a ton of compiler textbooks out there. Everything from the Dragon book classically to things like like there's this book, which I think well, this is the new edition, which I haven't read, but the older edition I think was sort of a classic. I don't know if this one is still used by anyone. Not very good, to be perfectly honest, in my opinion, but for a long time was sort of the only real place you could learn that stuff. I guess in the 80s, maybe to the 90s to some extent. When I was in school, although I didn't study computer science per se, I think the book they used at my school and a few others was the Andrew Appel book. Probably not the ML version, I think probably the Java or the C version. And this is the one superficial book that I think is good that I've seen. I don't know if this is still used, but I quite like this book. One thing I like about it is it doesn't spend too long on parsing. Traditionally, I think there's way too much focus put on parsing. Like, I'm kind of a parsing nerd, so I shouldn't say that, but for actually writing, like programming language compilers, you don't really need much in the way of theory. Like, you need some basic notions of lexing and recursive descent parsing, and that's pretty much all you need. You don't need to know bottom-up parsing techniques. You certainly don't need to know how to write like lex or yak, which is sort of like meta lexers and meta compilers, meta parsers. That stuff is very cool, and a lot of beautiful theory comes out of it, but not really necessary, honestly. And yeah, I remember this book is, it's not the best book. It's a little bit superficial, but it has sort of a good overview of a bunch of different things. But the book that I sort of think is hugely overlooked, because it's sort of old-fashioned in a way, is okay. So this is the edition. Is this one? So Niklaus Wirth, in case the name doesn't ring a bell, I mean, he's like one of the grand old men of computer science. Worked on Algol, famously wrote Pascal, designed and implemented initial versions of Pascal, Modula 2, Modula 3, and I think his greatest work, and which is largely unknown, unfortunately, is this whole system called Oberon, which is essentially an entire computer, including an operating system, a whole application suite, compilers, graphic systems, you name it, that I think was originally written back in the 80s after he had a sabbatical visit to Xerox PARC, where he used, I don't know if it was the Alto, but it was one of those workstations from the Xerox PARC folks, and basically came back to Switzerland, and with one of his colleagues kind of started to build that same style of personal workstation. And one of the cool things about the Oberon system is that, well, there's actually a book that covers it overall. Is it Project Oberon? What is the design of an operating system compiler? I don't think that's the latest edition. Oh yeah, this one. So yeah, you should go check this out. Like, it doesn't have all the source code in the book, but it has very extensive explanations of basically the whole design and a lot of the implementation techniques of the system. By modern standards, it's sort of old school, right? It's sort of like I guess for early 90s, it would have been, considered state of the art. There's still some parts of it that are honestly ahead of the current state of the art in some areas, like in terms of operating system, in terms of like interface design and the way the different, feels a little bit like Emacs in the way that all the different facilities are quite deeply integrated. But yeah, like one of the cool things about it is just his sort of aesthetic for computer science and programming is one that I very much find myself aligned to, which is this sort of notion that beyond a certain point, optimizing things or adding features doesn't carry its own weight, right? Like in a professional setting, you can justify piling almost any amount of complexity and extra code on a problem if it will give you 10% extra performance, if that's what sets you apart from the competition. But that's certainly never been his approach. He's always been happy to settle for sort of a golden mean approach to software design, and Oberon is sort of an example of that writ large. But anyway, um, I believe Oberon was originally written in Modula 2, um, and then rewritten in Oberon itself. So Oberon is both a sort of an operating system, computer system, but also a programming language, which is sort of has some features from Pascal and Modula 2, sort of a very cut down version of Modula 2 with some of the basic module system support, but without the full range of features on module, like on information hiding, and I think the type system is a little bit cut down as well. But anyway, so this book, uh, in some sense, a standard textbook on writing compilers, but doesn't spend very much time on the basics of regular languages and context-free languages. Just dives in, gives a really simple recipe for translating EBNF to actual code. So let's see if I can find some examples of that. Yeah, so like, he will do stuff like this. It's like, okay, here's how you translate eBNF to a recognizer, lexer. Um, so he has like a very to the point, straightforward approach to doing these things. And so like, the chapter on how to write basically any lexer is like 5 pages, I guess, or whatever it is here. And same thing with the parser. He uses very simple, one token look ahead, recursive descent. And I think so all that stuff is sort of like, I think, the right approach for an introductory class, but somewhat standard, I guess, at least among a certain class of people. I think the part that's not standard is when he gets to code generation. Basically, the way he writes this compiler, so this whole compiler that he presents is a single pass compiler, including all the different phases from scanning to code generation. But using especially this technique he calls delayed code generation, he manages to do a lot of sort of local optimization as he's generating code that would normally require either fancy IR manipulation or let's see if I can find that, or people optimization. But kind of his approach to this is like, hey, if you just don't, if you do a good job in the first place of generating the code, you don't need to clean it up later. That approach obviously has deficiencies. Like, for example, you can't really do fancy register allocation. You can only do something very kind of simple, but not too bad actually. Like surprisingly good for how simple it is. And I'm probably going to take this general approach in the compiler I write because I consider this sort of a optimal power to weight ratio for simple compilers. The stuff he does. Let's see if I can find the delayed code generation technique. The homepage, I mean, I can paste it, I guess. If you guys want to check it out. It's not prerequisite to understand what I'm going to go. I just wanted to advertise it because it's probably the closest to what I'm going to, like in philosophy and approach, it's probably the closest to what I'm going to do. Particularly his delayed code generation technique is sort of beautiful, like really a beautiful approach that really makes it easy to, for example, if you're handling an architecture like x64, you have all these very CISC-y addressing modes that you want to take advantage of. And a lot of the really like a lot of the kind of code generation techniques you might see in a normal introductory class would generally generate a bunch of really inefficient code that you would then have to either people optimize or use fancier techniques to clean up. But the way he does things with this delayed code generation technique, it's actually really easy to just exploit the x86 addressing modes kind of directly without any cleanup or pattern matching after the fact, by just kind of doing the right thing on the one pass through. I'm not going to go into too much detail about that. We'll talk about it if we get that far today. But anyway, yeah. So I would suggest checking this book out. This one is sort of a sleeper, underappreciated gem in my opinion. But anyway, yeah. All right, let's write some code. All right. I think I'm going to pull a bunch of this stuff. Okay. So this is the emitter. I guess let's write a simple lexer and parser for expressions just to get started. I do have a few minor tricks up my sleeve that might be useful even if you've written these things before. So the first thing I'm going to do is I'm always going to be parsing out of memory rather than out of a disk file stream. And part of the way I accomplish that is by you can either just read the whole file into memory the old-fashioned way, but I normally use memory mapped I/O, and there's a little bit of a trick that I will show you. I've tweeted about this before, like a year ago, but it's a nice little trick. So anyway, in our tokenizer, well, the most basic, let's call this the reader, I guess. One of the most basic things we need to do is we need to chew through a file character by character to scan it. And so what we're going to have is we're going to have a current character, and then we're going to have a remaining characters stream. And the convention is this is going to be null terminated the way a normal C string is. And that's going to be the case even if we're memory mapping a file into memory, which is where the trick I alluded to came in. So anyway, let's see. Right, so the basic operation is like reading the next character. And so first off, you can't read past the end. So we assert that, and then we so this is the basic function to read the next character. If you start reading from file, so this is the function to load something, and the way that's going to work, I mentioned memory mapped I/O, is we're going to do this we have to use Windows API stuff for this. So file name, desired access, generic, read, share is just, was it file share read, security no, create, open, existing, and then flags, file attribute normal, and 0. For now, I'm just going to do asserts rather than do proper error handling. I know that's not necessarily a good habit, but I'm going to do it anyway for the sake of this stream. So we have a file, and now we have to create a file mapping. Protect. So I believe, and this is where some of the tricks come in, write copy. So what is this actually set to? Read, write copy. So we're going to be able to do both copy on write and read write. Maximum size high. I don't believe we need to do that. And then create file map. What is it? Create map view of file, I think it's called. So file mapping, desired access. Offset high 0, 0. Number of bytes to map 0, which means all of it. Base address 0. File memory. You asserted file instead of file mapping. Oh yeah, good catch. All right, let's try that. Actually, let's also create a test file here. Okay, so that didn't work. I think maybe file map view. I think maybe this thing actually. You have to specify the size. Oh, okay. I thought it was the same set of flags from this. So this is file map copy. Okay, so that still asserts. Let's see what the error is. Other way around. Invalid parameter, most useful thing in the world. Oh, okay, so this is 0. So it's actually that one. Okay. Oh, right. Page write copy. That still doesn't work. Well, does it open the file? Yep, it does open the file. Okay, so that works. It's probably this. It can't combine those flags. Okay. We also need to get the file size. So let's just make some stuff in here. So this is, okay. Oops, should turn this back to non-hex. Okay, 10, sounds right. So now here comes the trick. So basically, if you're doing a copy on write mapping, which we are, the trick is that we're going to overwrite just the in-memory copy. We're going to overwrite the last byte of the file with a serial terminator, which is not naturally on the disk file, right? Like disk files are not serial terminated. That's really not a file system thing. That's just a C string thing. But we want it to be serial terminated for the rest of the system to easily have a sentinel value to act as a terminator. And so here's the trick, I guess, which is we require, as a matter of syntactic, as requirement basically, that the last character of the file, well, first off, has to be non-zero. And then the last character has to be a new line, because then we can basically we can eat the new line and replace it with our own thing. So that's probably going to assert. Okay, no, that actually works. But suppose we remove that new line. Now it's going to assert. Yep. Okay. For some reason you can't see the assert on screen. It tends to pop those up on my other monitor. But anyway, so we're going to make this a requirement for syntactic well-informedness, which means we can then cannibalize this using copy on write tricks to be the serial terminator, without, because the idea is that basically this would be ignored anyway by the syntax of the language, and so we're just going to steal it. But if this was like 9 or some other meaningful character, we couldn't steal it. You could try to have the lexer kind of have an overflow character that it checks once it sees, but this gets complicated. Easier just to make this mandate. So anyway, having done this, we can now say remaining characters equals file memory, and current character. Actually, let's just, you can just do this, right? So this is just essentially initializing. Okay. This is just initializing the reader state. So after this, if you look at autos, well, current character, remaining characters. Okay, I have a leading. Let's try that again. So first character is 1, the remaining is 2, 3, and so on. So anyway, so that's a little trick. Not always applicable maybe, but kind of nice to have. I'm going to put this in another place so I don't have to stare at it. All right. And for now, we're not going to worry about shutting things down and cleaning up. So yeah, from this point on, we're in business. Let's talk about tokens. I'm going to use a time-tested trick for encoding the token type or token tag, which is any single character ASCII tokens are encoded as themselves. So classical ASCII uses the first 128 values of a byte. We're going to use those to just encode themselves, which means that we can do things like if token equals plus, then do whatever. So that's like a standard trick, so you can do that. But then for things like like identifiers or other multi-character tokens, we will have we will essentially just we'll just have them subsequent in that upper range of the byte from 128 up. So that's the idea. Yeah. So okay, let's do a basic tokenizer. So there is a current token. We don't have multi-token look ahead, so this is fine. What we're going to do here, and then we have read token, and read token switches on the current character. By the way, end of stream is going to be indicated just like 0 means EOF in some sense, or that doesn't mean EOF, it means end of string. We're going to use 0 as our end of file indicator token. So if we ever read a character and that character is 0, we know we've reached the end of the stream, and so we just set the token to 0. If we have white space, okay, white space, like, let's see if I can remember all the stupid combinations. There's this one, new line, carrots return, tab, vertical, tab, maybe this is it. If we have this, then we essentially just we retry. By the way, you might wonder why. So let me just make a small note here about handwritten parsers and small efficiency things you can do that not everyone does. A really common thing to see people do is at the top of a read token function, they will write something like this. Something like this. And so this essentially just eats all the leading white space. Now this is perfectly correct, but it's a little bit inefficient, and the reason is, now admittedly this is probably going to be pretty well predicted a lot of the time, because most of the time you're not going to get white space, although maybe that's not true. I guess you have runs of white space that can be quite large, but in any case, you're sort of biasing the whole decision tree towards white space by putting this up front. Whereas if you have a single switch statement, it's sort of like you're getting the maximum amount of information out of that character all at once. Whereas if you do this, by the time that current character is not a space anymore, you now go in here, and at that point you could have dispatched directly to the right case. So anyway, if you do a single dispatch, then you basically have one switch statement per character for the main path through this thing. And I have to read character. Okay. And then we have I guess let's do a simple, okay, I don't know. Let's do a simple number parser. So in this case, we are going to, and this is another case of doing, getting the most out of your initial dispatch. So some people might then do this, while is digit, current character, do whatever. But we've already done the dispatch to figure out we have a digit. So this is not what you want to do. What you want to do is token integer. I'm actually just going to call this token rather than current. Right, so what we're going to do is we're going to initialize the token integer with current character minus 0. And then we're going to do the while loop. after having read the next character. For now, we're not going to do signs or anything. Yeah, we can use this as digit. It's probably fine. Well, as digit, then we do the normal reduction. Cast from int token. Well, I guess you can do this. Let's see, read. Okay, so let's try that. Oh, the other thing I should mention is when you do start reading from file, not only do you have to initialize the first character, well, so you have to do a read character, and then you have to do a read token in order to prime the pump, because we always assume that this is the next thing. So you have to initialize those. Let's see if that works. Did not work. What happened? All right, remaining characters equals file memory. And let's just step. I don't quite know why it's. Oh. Let's just initialize it manually. Okay. So that works. So we should just be able to actually just set a breakpoint here and then see what token is. So that's an integer, and this is, I believe, the correct number. Yep. Okay. So already this is enough to do a basic parser. Actually, let's call this start parsing file. So let's do an expression evaluator. Parse expression. Most basic case, let's start with that actually. If token is token integer, then we just return that value. Otherwise we assert for now. Okay. So result is the correct thing. Okay, let's put in a bunch of single character sort of self-quoting tokens. These are all in the category of things that are equal to themselves as a token. All right. Now, let's see. So I guess I should talk a little bit about expression parsing, and especially doing left recursive grammars with precedence climbing, which is what is the standard way of doing it handwritten. Very easy. So suppose you have a grammar that looks something like this. An expression can be a term, or it can be a term, expression plus a term. A term can be a factor, or it can be a term times a factor. And a factor can be an integer, or it can be a parenthesized expression. So this is like what I consider the canonical, you know, toy grammar that has some interesting stuff. And actually, let me maybe do it this way here. So some stuff here. So the interesting thing, by the way, is handling subtraction correctly, because that's sort of a naturally left recursive construction because of its left associativity. Right, so when you write AB minus, like this means this, right? You subtract B from A and then C from that and so on. Whereas the standard way of doing it sort of right recursively, which is the normal thing you do with handwritten recursive descent parsers if you're just doing things recursively, is naturally right associative, and then you're kind of fucked. It's very easy to handle, but I've seen some people kind of tie themselves into knots just dealing with that fairly trivial problem. So it's probably worth thinking about. So yeah, so let's do parse factor. If we have a token integer, that's great. Otherwise, if we have an open paren, then if you have an open paren, then you consume that and you recursively parse an expression. And expect token. So expect token is a variant of read token, which, so I'm just using assert in lieu of error checking, but we're going to go back later and do proper error checking. I'm just writing it out because I don't want to get sidetracked. So assert that token is the expected token, and actually I do kind of want to call it current token now. Assert that current token is the expected token, and then read the next token. So then we do that. And we also have to for declare because of the mutual recursion. If you're dealing, right, so let me show you how you do the left associative precedence climbing, because that's the thing where, you know, if you're sort of used to thinking recursively, then you fall into this trap where recursion is easy but iteration is hard. And if you're sort of from the C world, iteration is the thing you go to. Recursion is sort of something you do less frequently, or at least less naturally. So maybe for you it's not a problem. But I know that when I spend a lot of time programming in Scheme and Python and languages like that, I lean really heavily on recursion. It's a natural way of approaching a lot of problems. But this is one case where doing things iteratively gives you a nice bottom-up algorithm that's still very easy to understand. So yeah, let me show you the trick. The idea is the following. Oh, I can actually take the grammar and do some calculations on the grammar. So note that we have term. So yeah, the basic idea here is that we will well, let's see here. Let me just write it out and then explain it. It's probably easier. So you have a term. Okay. Can I convert? Maybe I should just make this an int. We don't have to do this crap. Okay. Right, so for now this doesn't really do anything, it just defers down to parse factor. Although, actually, let's already test it. So that's the correct result. Now suppose we surround this in parentheses. We should still get the same result. But we don't. Oh, it's because we haven't added rules for these yet. Okay, now we're good. Right, so this still works, and I mean you can have a bunch of these. Although, let's see here. So we should still get the same result. Although you'll note now if I don't close, we're going to get an assert. You can't see this; it's off screen. I really need to move the shit back on screen here. But anyway, yeah. So it's detecting the lack of balanced parentheses. All right. Right. So that's a basic thing. Let's talk about the expression parsing stuff with left recursion. The basic idea is the following: you parse a term, and then you say as long as the current token is equal to plus, for example. Then what do we do? Well, essentially we first have to consume token, and then we have to recursively parse term, and that's really it. Let's make sure that still works. So if you do 1, 2, 3 plus 4, 5, 4, 5, 6, I think that should just work. Let's see here. Right, so that's 5, 7, 2. That looks correct. Actually, let's do it like 3, 2, 1, just so it's something easy to recognize. Yeah, so that's 4, 4, 4. Now the thing about this is that you can't actually tell if it's properly left associative or not, right? Because plus is associative, so it doesn't care. So let's do something, I guess, trickier. Let's say 10 minus 3 minus 2. So that should be 5 if it's properly left associative. Oh. That's because I updated the parsing but not the semantics. So this should be 5 now. Yep, so this is 5. So like, note how simple this was. You literally just do this sort of, you know, you descend into the subterm and then you just look, you do this look ahead thing and keep doing stuff and reducing. This is what's called a left fold, like a fold L in Haskell or something like that. But it works really easily. You can use it with things that are right associative. So for example, what's an example of something right associative? I guess exponentiation, I guess, is right associative. Right, this is right associative. Let's do that. Okay, and what is the binding strength? Actually, let me finish doing precedence before we do more associativity. So then, you know, the thing you can do is, well, you could do a switch tape when you want to dispatch once. Now I'm doing sort of 2 dispatches, which goes against the earlier thing I said, but let's just do it for convenience for now. And then for the term, we do the same basic idea. So let's try that first and see if the precedence works out. Actually, I'm just set a permanent breakpoint there so I can easily return to it. Okay, so let's do 1 times 2 plus 3. Or, I don't know. So this is the correct interpretation. Maybe we'll do it like this. Let's see what that gives. So that gives 1, which is definitely wrong. So that's 3 plus, it should have been plus 2, so that should have been 5. So what did I do here? Oh, it's because this thing is not, I see. So operator token. guess it should be 5. It is 5. Compare this to, you know, if it did things like this, which we can try to run too, it will, okay, so that will be 5 as well. That's a little bit awkward. Let's do something else. Let's do 4. So the correct version of that should be 8 plus 3, which is 11. Whereas if you parenthesize it like this, it would be 20. Right? So anyway, so you can see that this deals correctly with precedence. And the reason it deals correctly with precedence is that when you start trying to parse an expression, it recursively parses as much as it can in parse term. And then basically what's left over, it looks for pluses and minuses and groups based on that. So in particular, if you're trying to parse something like this, if you do parse expression on this, it's going to start by calling parse term, which is basically going to gobble up this whole thing, because this thing here is going to parse an integer, and then it's going to see that there's a star, and then it's going to recursively parse the right operand of that, and then it's basically going to say, okay, now there's no longer, like the next thing after that is going to be a plus, but this thing says, okay, I don't know how to handle a plus, that's not me, I only handle star and slash, and so then it's just going to return what it's accumulated, and then when we go up here, then the current token is a plus, and it's going to take care of it. So that's sort of why the precedence hierarchy mirrors the call tree here. And as for associativity, so consider something like this. Like why does this correctly evaluate left associatively? Well, it's going to do parse term first. That's going to find just an A, and then next it's going to see a minus, and it's going to say, great, I found a minus. Now I'm going to essentially just have an accumulator, sort of left recursively, and then the next thing I'm going to find is a B in parse term, and I'm going to subtract that, so now we have this result, and then finally it's going to find another minus, and now it's going to do this. So anyway, that's the idea behind why this kind of iterative accumulator approach actually does the correct left recursive evaluation. So I don't think this, I mean, this is literally, if you've ever written parsers before, hopefully you know this stuff, but I see people get very confused by left recursion in expression parsers, and it's really, really trivial. So yeah, and you can also do this with tables. Like if you wanted to have an extensible grammar, it would be very easy to essentially, you know, you have one, you don't even need to separate functions. You could have like parse expression, and then with a precedence flag that bottoms out, and otherwise just, this is why it's called precedence climbing. It just kind of goes through the precedence levels. At every level, it looks for all the tokens. Like in this case, plus and minus have the same precedence, and so on. So yeah, this is like a very simple, I think it's called precedence climbing. Very simple technique. Yeah, this thing's like, yeah, so anyway. When you see it like this, it seems a little bit complicated, but this is how it actually shakes out in concrete cases. So anyway, where were we? Oh yeah, I wanted to show that right associativity works too. So let me just think about what the precedence is of this thing. So if I do plus this, yeah, so I think the precedence is actually really low for this operator. Like it binds really tightly. So I think we're going to have something called parse power, and parse power will essentially be this. And then instead, this will be parse power while current token. Well, I guess there's only one case, so we don't have to remember what token we ate. So we get a token, then we get the next, so let's call that, so that's the base we just read, now we get the power, and so the base is the value, and value is 1, and then value is accumulated like that. Okay, let's see if that works. Let's just make sure we didn't break the existing thing. So that still works. So we should be able to do like 2 to the 4. And that's 16, so that's correct. Now, let's make sure the precedence is not broken. If we do this, we should get, well, let's see, 16 times 3, 32, 48, 49, yeah, so that's right. So essentially this gets read as this, which I think that's correct. That's the normal precedence. It's very high binding strength. But yeah, so let's now test the associativity, which the associativity is currently going to be broken. Like, I can tell you that right now because we didn't set it up right, but that's sort of my excuse to explain to you how you do it correctly. Because this will be left associative, which is incorrect. So this will be that. Basically, this will evaluate as follows. So this is equal to 8 to the 4th, which is 8 times 8, which is 64 squared, right, which is 4k, versus the correct interpretation, which is this, which is 2 to the, which is a much bigger number, 2 to the 3 times 3 is 9, 9 times 9 is 89, 2 to the 89, which is a fucking astronomical number. So maybe I should do something smaller, just so, well, it's going to overflow, but let's do this. So that's 2 to the 8, or sorry, yeah, 2 to the 8 squared, so that's 256 times 256. That's, well, 64k. Was it really 4 before? So that's 8 squared, which is 2, yeah, okay. Yeah, did I really say 81? Okay, I'm really idiotic. Thank you. This is why clearly I need someone to help me with this very advanced mathematic exercise. So anyway, yeah, and so now it's 2 to the 3 to the, wait, 2 to the 3 times 2. So that's 2 to the 9, which is 512. So yeah, that's the difference here. So let's try evaluating that. Oh, sorry, not 64k, to 64. I'm pretty stupid today. Okay, so that's 64, which is an incorrect result. We want 512. So anyway, let me show you how that works and how it's different from what we've been doing. It's like a one thing you have to change. So note here when we recursively parse the power, we call parse power, which is sort of one level down. But if instead we do parse factor, well, first of all, let's confirm that it actually does the right thing. It does. So the reason that works is now it's actually recursive into itself, right? Meaning in the case we have here where it's like 2, 3, 2, it will first do the parse power, it will get the 2, then it will see the caret and it'll say great, we have something here. Then with a cursor where I'm currently at, it's going to recursively call parse factor, which is just calling itself, which is then going to finish this whole thing before it returns. So in other words, whereas before it would have done this, and then the recursive call would just have sort of parsed this much, and then it would have accumulated that, and then it would have seen another caret and accumulated that. This thing is going to see the first caret and then recursively do like this, get the result of that, and then accumulate using that. So anyway, that's how it works. And actually, because of that, you can also just do it like this. No? Yeah, you can. So in this case, in case it's not obvious, the reason you no longer need while in this case is that since you're recursively entering yourself, effectively you already have a while loop through the recursion. So it's actually inefficient and confusing to have the while. So, but anyway, so that's how you do that. So between these couple of things, you can now handle any associativity, any precedence. I haven't quite shown you how to handle unary operators, but that's very simple as well. Okay, so this is just an expression evaluator. Let's try to generate some code from this. Probably not going to generate code for the power case because fuck that. So let's see. In order to generate code from this, the basic idea is that we will essentially allocate registers to hold intermediate results based on a stack kind of ordering. So if you do something like this, you're going to do the parse term for this. The parse term is going to essentially emit the code that places the result into a given register. And then I know the result is there. I then have to, on my own, generate code to add 4 to that, wherever that thing is. So yeah. Let me just think about that for a second, how to structure this. Multiplication, by the way, is a little bit weird on x64 because one of the operands is implicitly RAX, and RDX is destroyed. So if you had stuff in RDX before, it's now gone. So you have to try not to use that, or if you do want to use it, you have to save the value and restore it afterwards. Okay, let's see. So we need a function that gives us the next register. Let's suppose we don't do any multiplications for now, just so we don't have to deal with the weird mul instruction and how it's hard-coded to use RAX and RDX. Same with div. Let's just do plus and minus. So in that case, next register is that a so we're not going to do any spill stuff, so we're just going to assume that Though we're not going to run out of registers for now. And then, let's see, what are we going to do? Okay, so we have to emit our I. Actually, emit move RI to the target register. With a current token integer. All right. The other thing I have to say is that the logic now is that we're going to return the register where you can find the result. So let's not even worry about that for now. Multiplier register. Well, we can't even do, okay. Actually, let's go parse, let's call this an atom. Or parse was a ground. Yeah, atom, that's fine. Let's just take this out of commission because we're not going to need it. As long as we're just doing plus and minus. Parse term. emit add. We're adding to target register using operand register. Oh wait, that's not how we write it. Emit RR. I think rather than doing this register allocation bullshit, I think the correct way to do it is just to do it down like register target. So you just pass that down. Even let's call this destination to be consistent with the earlier emitter code. We don't have to return shit because now it's implicit. We're providing it. Does not take one argument, right? So it has to take. So operand register is destination plus 1. Actually, I guess let's just call this allocated register. No. Alright, I didn't fix the code. So let's just do some simple math here, which apparently still doesn't work. Okay, now we're at the end. Why did it think it could keep parsing? So current token is plus. Okay, let's step through it. Oh. Okay. Let's go and run the old disassembler. There's definitely a bug because I'm overriding the register. Hey, I'm just using precedence climbing, which is the simple thing that that I think everyone does that knows what they're doing. If you're doing it by hand anyway. So why is this not right? So read the token, expect token, and then go there. Why, oh why is... Did I not maybe test this one very much? No, that's certainly not it. Yeah, that's the one. I mean, I have some code here, but like, I would actually say the thing that makes it interesting is the way it handles self-recursion, which is using iteration rather than recursion. Okay, why am I not generating the right code for this? B8. Oh, I'm never actually emitting direct. Let's go and look at this junk. B8. This one. I see there's a register and then, okay. Okay, that completely fucked things up. So this is the register. What did I screw up here? So it needs the register there. RD. I guess this is not the /R stuff. Oh, the lower 3 bits of the opcode byte is used to encode the register operand. I see. Oh, that's interesting. So I actually have to do this, right? Alright, here we go. So do this, do this, do this. And you can see we're now reusing RCX. And now we're adding that in. And now we're doing that. Okay, so that looks good. Alright. I guess let's add some stuff for subs. So the RRM case is 2B. 2B. And then the flipped case is 29. And then the immediate case is 81 with a extension of 5. Okay, Visual Studio. One thing I don't like about auto indenters is that when they go off the rails, you just want to kill yourself. Okay, let's make sure I didn't break anything. That still looks good. Now I guess let's do something like this, where there's a little bit of mixed associativity going on. So let's see. Yep, and then we add 1 to 2, that's good. Then we subtract 3 from that, which is good. Then we subtract 4, again, that's also good. And then finally we add 5, which is good. So this all looks good. Alrighty. God, do I want to do multiply? I kind of have to. Multiply is a pain in the ass, though. I think... let's get the list here. So we don't, I think we don't want to use RDX if we can help it, because it'll tend to get destroyed by multiplies. Maybe that doesn't matter. We have to deal with the general case where all of them are in use anyway for really deep stacks. Yeah, let's just keep it like that. The thing that's awkward, I think we have to do exchanges. Like, oh, let's just fucking do it. Stop whining. okay. So the thing that's awkward is that if destination is not RAX, then we have to do some exchanges. So let's go and implement those exchange things. Was it exchange. Okay, sorry, I was just responding to Sean on Twitter. So yeah, exchange, so 87 for this one, and then the reverse case is this. Oh, I guess they're actually symmetric. That's funny, I hadn't thought about that. That makes perfect sense. Alright. So, if the destination is not RAX, then I think you have to generate an exchange from the current RAX to the temporary register, and then move also if so the other thing I have to do is since mul will override, it will write not just RAX but other stuff as well. Well, actually, so first off, let's this is probably hugely efficient, but we're going to do it anyway. What's going on with these fucking things here? So, okay, God, stop it. I have to go and configure. I don't know what settings are fucking what my braces here. Okay, so let's see. Swap the old RAX into a temporary because it may be in use. Which, by the way, is an argument against allocating things first to RAX, because it means that if you're doing multiplies, you'll often find yourself not being able to use it. But anyway, so move that out of the way, move the new thing in there, do the multiply, move the result out, and then swap things back in. Actually, I don't know why I did an exchange. That's fucking weird. Okay, there's no temporary register. Okay, let's see what happens. If I do 2 plus 3. So if I do this case, then it should be able to do everything in place with RAX without doing any temp swapping. Okay. This is fucking garbage. Oh, I guess I didn't update the expression function. Okay. This looks reasonable. So now RAX has the new value. And we can just add this on. So this is actually like, I mean, aside from the fact that I'm using these super long immediates for no reason, we could use 8-byte immediates here if we wanted to, which I'm not going to change right now. But yeah. So okay, let's try the other case where we've already like this basically. So in this case, RAX is already taken up by 1. Yeah, I think we already get in trouble here. So 2, 3 have to be multiplied. We put RAX into RDX as a temp register, but that's totally wrong because we haven't consumed that yet. It's because I don't do operand plus. Okay, so it uses RBX for the temp, moves RCX into RX, does the multiply by RDX, which is now destroyed, moves the result back in RCX, restores the temp value that we killed, and then no, the order there is wrong. Then add. All right. Okay, so there's one bug right now because I protect RAX against destruction, but I don't do the same for our DX. RAX copy. This is really redundant, of course. This is kind of weird because if this temp register is RDX itself, then we're essentially doing something pretty roundabout. Like a lot of this stuff would be faster in the common case if we allocated other registers that are not destroyed for this crap. In fact, I guess we can do that. So let's go back to the original register allocation order. Like, Okay, so let's assume we can't actually use these. So these are always free. I have a feeling this probably is not the right way to organize it. But let's try for now. Okay, so for multiplication, step 1, we move destination into RAX. Step 2, do the actual multiply. And then put it back. Okay, this is broken instructions right here. So R15 should be fine. No, but even the first one was broken, so I think that's actually move RI. Aha. Okay, that's better. Although I don't know why it's using RDI. Okay, there we go. So move a bunch of things in. Move R14 into RAX, do the multiply. Having done the multiply, move the result back where we need it in 14, then added to that. It's now in 15. Great. So that looks better. Oops. I feel like the way I wrote this was sort of a regression. Get next register. So it seems like there should be like first temporary register R15, and then there should just be a next temporary register. Well, actually, let's actually, I can just do a subtraction. so that handles that case. Let's do division. for division, let's go look at the Intel manuals. Okay, so let's say plus 5 divided by 10, or 10 divided by 5. 8 by 4. So R14 is 8, and we divide by that. Okay. I think that's good. Oh, you're making a disassembler? That's cool. I've been thinking of making one too. I've been kind of working, like some of my streams have been on stuff like the Sino thing, which is sort of one, I guess maybe one half of the hard parts of a debugger. You know, you kind of need a disassembler for a debugger, even just to be able to do good stepping, and then you need a way to interpret the data, so you can do expression evaluators and stuff like that. And so I've been kind of working my way towards doing a stream on writing a disassembler and a debugger from scratch, using some of those pieces we've already written before. But yeah, for today, let's I'm sticking to a compiler. So maybe this is a good time to just take a step back and note how fucking, I mean, can I say nice? But this is fairly to the point code for what it is, right? If you look at I think if you look at the code here, you know, it's fairly tight kind of byte packing code, except for the assorts. Let's just remove those. But yeah, check this out. You can see how it's basically done some full keyword moves in order to store in the next opcode. So even though we're kind of writing the code at a fairly high level, I mean, sort of assembly-ish level, the actual code being generated is just pushing full words into the code buffer, which is what you want to see, right? Why is it reading this back out? Oh, this is the pointer, I see. Yeah, doing x87 sounds like shit. One of the nice things about x64 is not having to worry about that. Okay. So next thing I want to do, this is sort of veering towards the Viert delayed code generation technique I alluded to earlier. So if you look at this code right now, you'll notice that it's not really using x86 addressing modes very well. So for example, in theory, I could do all this stuff like the adds. I could do these with immediate operands rather than rather than putting them into registers and then using the registers. So this is sort of a more RISC style of code generation where everything has to go through registers. You cannot directly deal with immediates, for example, or more complex addressing modes. So that's something that, you know, traditional techniques for doing this, you can try to do peep code or a peephole optimization, which is basically just a sliding window sort of pattern matching technique, not the greatest thing in the world. You can try to use a higher level DAG representation, so you can kind of have some non-local information about how the data flow is and then generate something more optimal based on that. Or you could just do what Niklaus Viet does and kind of, well, I mean, let's talk about what this does. So the idea behind this technique is so right now we're passing a destination register. Suppose that rather than interpreting that destination register as a hard sort of requirement on where the result has to be put, instead we basically take it as a strong hint that, like, hey, this thing is available. And then what we do is we create a struct which has two types, operand register, operand immediate. I wish that wasn't a reserved word. It hurts my heart. But anyway, so the idea is we're going to now produce operands which basically describe where we put the result. And so the idea is if the result is an immediate, rather than generating code just at the, you know, so what's an example? I shouldn't put that here, I should put it further up. suppose that, so right now in parse atom, if we see an integer token, we immediately generate this, we put something into a register. Suppose that we don't do that, but instead we just return essentially a piece of data that describes the intermediate or the immediate, and then anytime someone needs to use it, we will we will essentially we may put it in a register if we have to, if there's no addressing mode involving immediates, but a lot of the time we'll be able to just directly pick an addressing mode for our purpose. This will also let us do things like constant folding by just essentially processing things. Like if we have, for example, an add of two immediates, we will just fold them into a single new immediate operand with the summed immediate values and so on. So this is sort of a way that you can do a bunch of kind of on-the-fly one-pass optimization. I'll just leave you guys to think about that for a second while I go to the bathroom. Okay. So, I guess one question is, should we return it as a value or pass it as a register? Arguably, you should even, yeah. So let's do this. Um, the other thing you sometimes need is convert operand or materialize, or what's the right word? Convert operand to register. So if operand type is operand immediate, feel like there's something I should decouple here, which is the operand structure from what the next free register is. Yeah, that's right. That's the idea. Let's call it move operand to register. Okay, so this should generate the existing code. I'm just trying to set things up in a way where the old code and the new code are essentially the same. So 1 disappeared. 2 times 3. So that's 2 times 3. Happens correctly. And then put it back in our, and then add that. Add that to RCX, which is not even filled in. Where does RCX come from? What the fuck? So oh, that's definitely not right. So that's one of the errors. So move to that register and then register the fact that we did that. If it's already a register but the thing is not in the right slot, then we do a move and update it to point to there. Okay, so we're still not getting that first immediate, which is one of a couple of signs that stuff is very wrong. Okay. So far we haven't made any progress, but I guarantee you that now we're going to well, let's see if it's already in a register. Okay. Okay, this is where we can do some magic. So right now we're doing this emit move to register, but we don't have to. So that's where the magic happens. Suppose we now do if operand type is immediate, or let's see, if it's a register, then we do this, just as basically the same as before. But rather than forcibly moving things into registers, even if they're immediates, we can also do this. So we can do that in both cases. God, the indentation is completely hosed here. I have to go and configure that after the stream is done. Conversion from immediate loss of data. Yeah, that's, I guess, a problem. Actually, let me... For the sake of simplicity, let's not deal with that right now. So, okay. We're still not doing the thing. All right. So let's do a simple case. If I do this, then what I want to see is essentially just... okay, so that works. So now that's using immediate operands. What if I do this? That works too. No. Well, where's the 3? That's troublesome. There should have been a 3. Instead we got a 1. So this is 2. Oh no, this is 1. It's 2. Now we're back to 1. What? Okay, better. I think it was just... But yeah, okay, so that works. Okay, let's now start doing real magic tricks, I guess. If so, we want to do constant folding. So to do constant folding, let's see. If the first term is an immediate and the second term is immediate, then we just fold that into the destination. Which means we don't want to materialize this as a register too early. We kind of want to wait. If destination type is immediate and operand type is immediate, otherwise you can do the same shit for this branch here. Okay. Did you guys notice it disappeared? It's because it's optimized out completely. So there's just going to be a, yep, operand immediate of 6. So that completely constant folded everything. So this is 2, which is 6 minus 4. So that's right. The other idea I had is you can do copy propagation pretty easily with this stuff. So right now, well, maybe that doesn't work in this case. Yeah, let's just leave it like that. I also don't think there's any multiplies and divides only work with register operand, so I don't think we can get any leverage there. No, that's not true. No, that is true. Okay. Yeah, no, I know everything can be constant folded to a single constant. That's why the fact that it works is a confirmation. But actually, since not everything works that way right now, you can try to do something like this, and you're going to see a mixture. So for example, if I do this plus 7 plus, and then on the other hand here 9, you should get a mixture of folded and unfolded code, since right now the multiply and divide doesn't do folding. So yeah, you can see the 8 is folded here. 2 times 3 is done sort of manually, so this is 2 times 3, and then it just adds this in. Although, interestingly, it shouldn't have to materialize that there. I think it's because it's on the left, and it doesn't exploit the fact that it's commutative. Yeah, I guess that's a weakness of this approach, so we have to fix that. I don't know if that's better though. If you're using this sort of stack style register allocation, I think that's actually fine. So if we do an add and both of them are like this, then we do the folding. Let's reorganize this code a little bit. If the destination is an immediate and the operand is a register, then we can actually essentially do copy propagation through the system. RI, and then do that, and then destination, operand immediate. So yeah, you can't do this with subtract because of the operand order. Actually, that's not true. Ah, that's an annoying warning. Right, so now the 8 is not in a temp register. 2 times 3 is done manually because that's the way it works. Then we do the sub by 4. Why are these not folded? Why is -4? Oh, it's because it's not -4, it's -4 and then +9. I can think of a way you could fix that by making things right associative, but that's probably a little bit cheating. Oh, that's wrong in this case anyway. Okay. Okay. Does anyone have questions so far, by the way? I'm starting to get into some more of, I mean, it's not advanced stuff, but it's kind of some trickiness using this notion of operands as a way of delaying code generation so that we have more context on the data we're dealing with before we make a decision about actually generating code. Okay, so let's go and give the same treatment to some of the other things. So let's just replicate what we had. Right, so I guess let's not do that. If we have two immediates, then we just fold things. Same for that. If otherwise, yeah, so there's actually no other case, I guess. Oh, actually, that's not true. If one of them, if this is an immediate, this is also a place where you can do strength reductions and stuff like that. Let's just do the dumb thing though. Actually, I disagree that optimization would be a lot easier if it wasn't single pass. The kind of optimizations I'm doing here are actually, I would say, just as easy to do single pass as not. Like if you had an AST or a control flow graph or a data flow graph or anything like that, the stuff I'm doing here is not substantially easier. The stuff that's easier with more structure is things that require multiple passes or things that require a backwards pass or something like that, because you're kind of forced to look at things in the order they appear in the source code, more or less. Anyway, let's see if that works. So what changed? It looked like one thing changed. 1.7. So 8 is there. For the multiplication itself, 2 times 3. 2, 3. Move that in, multiply by R13, which is 3. Move that back out. Oh, and there's another mol. Okay, so... Oh yeah, that's no good. Okay. Seriously? Did it blow the undo state? What in the world? I don't think I've ever seen that before. That has to be a new bug. So it fucked up my code and then it blew away the undo stack. Thank you. 10 out of 10. Did it completely wipe away parse term? Are you fucking kidding me? Oh my god. Okay. Time for source control. I don't even remember half of these fucking switches. Mm. Oh, you're right. I thought for some reason... Okay. I'm just literally going to check in everything because... Oh, this is going to be a disaster with... No, let's just do it. Okay. Do I really have to fucking recode this thing? Jesus Christ. skip the token, create a new operand, a register to go along with it, get next free register. Parse term like that. I swear after I reinstalled Visual Studio 2015, maybe there's like a new service pack I accidentally installed in the process. But it's gotten super weird. Okay, that's totally not what I wanted. Okay, there's nothing fucking here. Oh, it's because it's totally folding now, I guess. Which is kind of working as intended. So that's, let's see, 19. Let's do the math. 6 plus 7 is 13, 14, minus 4 plus 9 is 19. Okay, so that's correct. Okay, just to make this, I guess, a little bit more interesting, because now that it's folding everything, we don't really have a good way to do anything else. Suppose you do R1. We have a bunch of temp registers. And actually, we can just call them like XYZ. And then actually, let's just say this is a register. Current token register. And this is like maybe RCX. This is not RDX. It's like, God, what's the ordering? CX, BX, RSP, RBP, RSI. Okay. RBP, RSI. Oh, read character. Man, you guys are eagle-eyed. Still be empty. Yep. But now, if we add in some stuff, like minus 4 times x plus y divided by c. Boom. You see this shit? Look at all this constant folding. It's amazing. Is it? That actually looks weird. So this would be 8. So it folds all of this. There's too few constants. What the fuck happened to all the constants? Is my constant folding just too good? I suspect not, because there should be at least 4 times x should do RSP. No, you're right. That's a little weird. I wonder. Yeah, why is RSP being used like that? I'm just starting to think about. Actually, so let me reduce to a simpler case. 4 times x does what? Yeah, so it's the RSP that's supposed to be an immediate but isn't. Or actually, it can't be an immediate. It has to be materialized into a register. If I do this, what then? Okay, that works fine. Oh, I know what it is. No. RSP does have a funny encoding, but I don't like. Let's just go back to this. Oops. What you would expect to get generated here is something like. No, this is good. Move stuff to RAX. Ooh, I think I know. It's almost like this one isn't doing its job. Right, like this, there's actually no guarantee that the thing here. I see. we should make sure that destination is always a register. So if this is an immediate and this then we certainly can't do that. We can do what's the correct way of handling this? So certainly in that case, the operand is a register, and we should put the result there. We should do it like this. Wait. So put the operand in RAX, multiply by this, and then move it back out. And then say the destination type is now register. And like that. Otherwise, they are both registers. Okay, better. Let's go back to this complex one. For an RAX, multiply by RCX, which is X. Then put this back in RCX. To that, add this thing, which is a, well, let's see, what is it? -1 is FFF. And so this is, yeah, okay. And then move this into R15. I guess one thing that's sort of philosophically wrong is that we're kind of overriding RCX in place, whereas my whole notion of these XYC is that they kind of represent permanent registers, not scratch registers. So that's actually a bug. Oops. Alright, so we're going to do this. So now RCX never gets overridden. RAX is scratch, which is why we don't use it there. Do this. RSI. RSI is scratch. Okay, so we need to do the same thing for div. That is still weird. So RSI, I think, is... Yeah, so RSI and RDI. And then it says after it's done, it moves it back, but that's, yeah, that's not kosher at all. I guess that's sort of the general... Yeah, actually I see why that's happening. Because it doesn't distinguish between temporaries and permanent things. Oh, token register. Actually, you know what? Instead of, yeah, so this is a good chance to start doing stuff related to stack frames. So rather than just treating them as living in registers, let's say that variable, that they actually have an offset. And it's like an RSP offset or something. Variable offset. And so in this case, I guess let's just say it's 0, 8, 16. And actually, let's not even do offset. Let's just do them sequentially, and then we can do the multiply ourselves. This is like a logical stack slot index or something like that. So if token variable, and we have an operand that's a variable, and this is what that looks like. And this is a x64. Okay. I should make sure there's always a fallback here, because now it should assert. Yep. Because now we can say, hey, is this thing a variable? And then we can say, what's the offset? Well, it's this one times 8. And then we have to put it in target register. So what we're going to do is we finally get to use our fancy addressing modes that we spent a long time putting in. So we do something like this. And let's see, emit move rsib. So yeah, sib and then rsp. No, so it's actually, yeah, so the way you have to do sib, you have to do that like fake. Let's do it that way. You have to do that fake mode with the RSP as the scaled index, which is not actually valid. Do the scale directly in there too. Oh yeah, that's a good idea. Nice. Wait, that's not... Well, I guess if I put the thing in a register, but this is like a constant. This is actually just a displacement. Yeah, let's do it this way. In 64-bit, I don't think there's a way to do indirect. You can do... Actually, let's do RBP, because there is a way to do that. So I think if we do RMD... So where did I forget to close my definition? Oh. Okay, compiled. Didn't do anything I wanted. Okay. So what did I do wrong? When Someone requests a move to register. I mean, it could be that I'm just screwing this up. Let's try something else. R sub D. No, it looks like none of this is ever getting generated, or at least not doing anything useful. Yeah, this is never hitting. What the fuck? Okay. So this is token variable. Which means we should be hitting this case a lot. So this is 0. So now we go in here. I see. This whole matrix is not exhaustive. What's the best way? Well, the thing you can certainly always do, I believe, yeah, let's do that as a backstop. No, that's not. Doesn't even work because this could be here. Yeah, you're right. It's probably better. That's probably going to work, actually. Nope. Well, the first, I guess the problem is, in that case, it's going to not even emit code. It's just going to return a descriptor, which says this is variable 0. But yeah, okay, so we have to think about these different permutations for the code generation in a way that doesn't get completely out of control. So multiply is actually the wrong place to start for that. A better place to start is like 1 plus x. It's doing the wrong thing right now, but okay. So if you're doing 1, here's your constant folding case. If this is an immediate, then, so what are you doing? You're adding that to the thing. So emit move to register. So I see. So basically the post condition of this is that the thing you're pointing to is in a register. And so in this case, if the second operand is a variable, this will load that thing into the register. It will then add this onto the end, producing the result there. Okay, so I think that should handle that case. Yep. Otherwise, we may have to the other thing I didn't realize before is that this doesn't have to right, so okay, I see, so I think this is a better approach. The post condition of move to register is not that it's in the given register. The free register is just like a hint. I'm just going to move through the cases and make sure we don't have any mistakes here. So emit move to register, but then read operand register. That's the important part. We can't directly assume it's going to be in free register. Okay. So let's make sure that still works. So that works. What about this one? So that works. Oh God. Free me from this insane. Well, let me just go and fucking fix this shit. Okay, here we go. No more bullshit, hopefully. Okay, so now we do this. This is awesome. We can also do this. And that doesn't work because I'm a copy and paste moron. So for the subtract, we do this. And then when we flip the operands, we have to negate it. so x minus y, which is correct. Emit, add, okay, so this is all good. I think we have to give the same treatment to multiply. So in this case we have to emit move to register from here. Okay, so let's try this. So RCX goes there. Oh, this is broken because we're not allowed to put that back. Oh, it's because I do it here. Oh, I did it for one but not the other. This is multiply. Emit move to register. So it's already in a register, which is great. Okay, so right, so you can see that. Why is it using RDX? It should be. It's also not doing divides. Oh, there's no divides right now. So for multiply. So this should be. Oh. That's a stupid typo. Okay, this is better. Read from these stack frames. Although we could have done that directly here, but okay, I have an idea. Emit move to register should be emit this would be like registerize. So this is the one that just gets it as a register. There's also move to just emit move to register, which really should have a hard constraint. So this is not a target register, this is a free register. Okay, the reason I think that's useful is that, let me show you some tricks, I guess. This is one of the nice things about this approach, is that so operand emit as register. But like, so in this case we know that we need destination to go into, like whatever it is, it needs to go into that register. So we can just do that and curtail this. Yeah. So I don't even need to say this, I think. Well, let's think about it. So we can do constant folding in this case. Otherwise, emit in some way things to, I should say, move to register. You only want to do it if there's a reason to. So in this case, have to get the destination to RAX somehow. Then we have allocate operand to free register. If it's already in a register, that's fine too, then we just use it in place. Then when we're done, we move this back to free register, we assign that to the destination. I think that's good. So yeah, do you see how, well, was this happening before? But in any case, we're directly, yeah, I think we were, but no. I think previously we were moving this into a temp register, then moving it into RAX. Now we're directly moving it there. So multiply these, move the result out to R14. Move stuff in here and then subtract. Yeah. So we can do the same shit here. Okay. Let's do some c divided by x shit. So let's see here. So move C directly into RAX, move C into R14, do the division, move it back out to R14, and then add it to R15, which is the intermediate result. Yeah, so that looks good. And you also notice by using these sort of functions that establish post conditions, we also reduce the case analysis to quite a bit fewer, and it makes me think that we should go back and do the same for add and divide, unless there's something about them that prevents it. This is already pretty reduced. Hey, thanks for coming by. All right. This is already pretty good. I think I'm going to take a break and come back later tonight. I'll just spend the next 10 minutes just going over what the next step should be. So we have code emitting and sort of on the fly optimization for a bunch of cases now. Might be fun to do a quick I a quick strength reduction. Check operator precedence for errors. All right. Thank you, compiler. So let's just do it the slow way. Is that right? So one would start at 0. So log 2 of 1 is 0. I think that's right. Okay, so I meant multiply. So basically, if sorry, let's just say one of the operands if this is an immediate and the immediate value is power of 2, then emit as a register. Then we have to do some shifting. SHL. Why is it a double precision? Oh, here. So shift left. I don't think we use these. Anyway, shift left by yeah, I guess it doesn't make sense to do a shift left by anything bigger than a byte. Okay, let's stub in a very specific emit RI. I'm just going to special case one of them. I want to fill in the full matrix right now. Up one. So left shift. C1. C1. Let's see. C1 04. So Josian asks, in parse atom, do you defer emission of constants but not expressions so you can fold later? Yeah, that's basically the idea. It's not just for constant folding, it's also for address mode folding. So if let me give you an example. Suppose I write x plus y, what's another example? Yeah, 3 plus x. Ideally, I just want to store this as move dest RBP plus x offset add dest 3. And in order to do that, I have to not prematurely put everything in dedicated registers. I have to delay the materialization as registers, because the naive way of doing this is sort of like temp 1, 3, temp 2, you know, x offset, and then maybe even like, oh, now we have to move this over here, and then do something like this, right? So this is what I'm writing here is the kind of code you also tend to get from, like, if you're writing your own if you have your own like stack machine VM and you write like simple stack code, it will tend to have this kind of shape here, where it just sort of generates things in isolation, and generating these intermediate operands that describe the result but don't necessarily materialize them eagerly means that by delaying things a bit, you can make better decisions. And it still works with a one-pass compiler. So that's sort of the idea. There's a little more to it than that, but that's the overall intuition. Okay, so what did I add? Emit as register. So now destination is in a register. I just want to do a shift left by log2 of operand immediate. Oh yeah, this is, I think, a bug. Is it? No, it's not. Yeah, that's right. So emit as register. Emit. SHL. Oh, it's one I. Emit function does not take 0 arguments. Oh, right. Okay. Let's see if this works. Let's make sure it didn't break shit. Okay. So let's try doing like 4 times x. Actually, right now I don't handle. I only handle when the second operand is a power of 2. So let's do like 8. So this should be a left shift by 3. Yay! Magic! Look how easy it is. Okay. So left shift by 3. And then we can say divide by this. should really have a way of kind of switching the roles of these without repeating the code. But I will repeat the code for now. So if the destination is an immediate and is the power of 2, then we will emit the operand as a register. No, you can't actually do that. Actually, you can because it's commutative. So you can only do it with multiplies but not divides. So that's another reason to keep those separate in that case. So in this case, the operand register goes like this, and then the destination type is operand register. And so that does that by 3. So now if I do this, I should be able to get the same thing. So that still does the same thing, even though now they're reversed. On the other hand, I can't do this, right? Like, this is not a thing. I mean, you can certainly generate the code for it, but there's no strength reduction possible. So you can see it has to move it into RAX, and divide by that, move the result back, and then add it. I wonder if you could do... Yeah. In theory, you would think that rather than moving it to R14 and then adding, you can add RAX directly. I think the problem is with the stack-oriented thing, we don't know that RAX is going to be alive by the time we have to do that. So it's a little bit of a concession. But anyway, this is, I think, pretty, for how simple it is, this is, you know, it's sort of like non-idiotic code, basically. Like, it doesn't do a lot of stupid stores and loads and inefficient use of addressing modes or anything like that. Okay, I think I'm going to take a break. I will be back tonight, I hope. Otherwise tomorrow, but probably tonight. And next steps, honestly, I could have gone and filled in the rest of the language, but for me this part is more interesting than building, you know, full statement language, function definitions. Like, that stuff is important, but in terms of the overall structure of the code generator, this is probably right where it should be. I think the next step is probably to start doing statements and you know, other kind of imperative things like loading and storing variables. And then from there, control flow is going to be sort of a big, well, hopefully not too scary, but a little bit bigger subject in terms of the code generation, how you structure that, because you're going to need to do backpatching and things like that. So anyway, thanks for hanging out. Hopefully you picked up some tricks and saw how easy things can be if you kind of do them straightforwardly. Maybe actually, well, maybe tonight I will do a benchmark if I have like a huge... Hey. My voice is barely audible. I'll try to turn up the sound and yeah. Yeah, I'll try to fix the audio. I'm sorry if things are that bad. When you say the pings my computer makes, do you mean like when I'm typing, or do you mean like the system sounds or something like that? The other thing I'm worried about turning up my voice volume is if all my weird like mouth sounds and heavy breathing become too obnoxious. I'm worried about that too. So let me know what you guys think I should do. Maybe I'll just start speaking up more rather than always mumbling when I'm doing this stuff. But anyway, yeah. All right. I'll try to listen to the stream recording and then do some tuning on the sound. So that's good feedback. I appreciate it. Anyway, anyway, I'll be back later. Thanks for hanging out.